This is part 2 of lecture 15 and is continuation of our discussion on feedback topologies from part 1 of lecture 15. In part 1 we introduced the different feedback topologies and their respective the amplifier types for different feedback topologies. In this part and in the next part of this lecture, we uh, will discuss how to analyze the different feedback topologies and what are the pertinent features of these different feedback topologies. First, to refresh our memory, we'll review the names of the different feedback topologies that we have already discussed in some detail in part 1. So the first feedback topology that was introduced is the voltage sampling, voltage mixing, series shunt feedback topology. So in this feedback topology, voltage is sampled at the output and the feedback network produces a voltage signal at the input side which is mixed with the signal voltage. So both at the output and the input side signal is in the form of voltage, and it's also known as the series shunt feedback topology, which indicates the type of connection at the input and the output side. The second feedback topology that we introduced was the voltage sampling current mixing feedback topology. So in this sample again the voltage is sampled at the output, and at the input side the feedback network produces a proportional current which is mixed with the input signal current, and the feedback topology is also known as the shunt feedback topology that indicates how the circuit is connected at the input and at the output side. The third feedback topology introduced was the current sampling, current mixing feedback topology. So in this feedback topology, current is sampled at the output, and the feedback network it produces a proportional current at the input side which is mixed with the signal current, and this feedback topology is also known as the shunt series feedback topology. The last one, the feedback topology, is the current sampling, voltage mixing. Again, at the output side, current is sampled. Feedback network produces a voltage signal at the input side, which is mixed with the signal voltage. And the feedback topology is also known as the series feedback topology. This is how the circuit will be connected in series both at the input and the output side. So these are the different feedback topologies so that were introduced in part 1, and here we'll see how to analyze these different feedback topologies. We're starting with the voltage sampling and voltage mixing. So in this part mostly we'll discuss how to analyze these the first feedback topology. Next part we'll see how to analyze the other one, the voltage sampling and current mixing, and the other two, once you know how to analyze this, then you can also do it by yourself for the rest of the feedback topology. So this is the block diagram representation of the voltage sampling voltage mixing feedback topology. As you can see, at the output side voltage is the feedback network is sampling the output voltage, and it is producing a feedback voltage Vf at the input side, which is mixed with the signal voltage. The difference between Vs and Vf then goes into the voltage, the basic amplifier, which amplifies this difference signal Vi. So at the output side, the connection is shunt connection, and at the input side it is a series connection. So this type of feedback topology is also known as the series shunt feedback topology. Now we want to analyze this feedback topology, determine its different parameters, starting with the gain of the feedback amplifier. The gain of the basic amplifier is in this feedback topology. The signal both at the output and at the input side is in the form of voltage. So the configuration of the basic amplifier is a voltage amplifier. The gain of the basic amplifier is defined as V0, the output voltage, divided by Vi, the input voltage of the basic amplifier. Then the gain of the feedback amplifier can be defined as the V0, the output voltage, divided by Vs, which is our original signal voltage. That is our overall gain, or gain of the amplifier with feedback. Now here our main aim is to determine first if the other parameters of this feedback amplifier are the input and the output resistance. Apart from gain, the most important parameter for the amplifier is the input resistance and then the output resistance. So here we will also see how the feedback influences these two parameters, input and output resistances. So Ri and R0 are the input and output resistances of the basic amplifier. Then we define the input and the output resistances for the feedback amplifier. RIF here is the resistance in from this part of the circuit, that is we define as the input resistance of the feedback amplifier because it includes the feedback network, and this is the actual resistance that will be seen by the signal voltage Vs. And the ROF, the output resistance of the feedback amplifier, is resistance seen from here, that includes the feedback network, and that's why this is the output resistance with feedback, and this is the actual output resistance that will be seen by the load. The load will be connected at this point, and that is the output resistance with feedback. So apart from the gain of the feedback amplifier AF, will be also investigating how the feedback at the input and at the output side will affect these amplifier parameters, the input and the output resistances. So first we'll be interested in to find the gain of the amplifier with feedback AF, which is as we have already defined, the gain of the basic amplifier V0 by Vi, and the feedback factor, the other important parameter that is needed to determine the gain of the feedback amplifier. Feedback factor here is the output of the feedback network, that is Vf, divided by input of the feedback network V0. So that is our feedback factor. Now these two parameters, one is the gain of the basic amplifier A, the other is the feedback factor of the feedback network. These two parameters will determine the overall gain, or gain of the feedback amplifier. So we start with the difference voltage Vi. The difference voltage Vi can be expressed as the difference between Vs and Vf. So Vi is Vs minus Vf, and the Vf is the output of the feedback network. And from the definition of feedback factor, beta is Vf by V0. So that means Vf we can express as beta V0. So Vf is beta V0. Now V0 is the output of the basic amplifier, whose input is Vi. So from the definition of the gain of the basic amplifier, A V naught by Vi, V naught is A Vi. So substituting V naught for A Vi, finally we get this expression for Vi. Now rearranging the terms here in this equation, we can express Vs as the summation of these two, and which we can express like this: Vi times 1 plus A beta. So this is how we express the signal voltage Vs in terms of our input voltage or the difference voltage that goes into the basic amplifier, input of the basic amplifier. So now we can write the expression for the gain of the feedback amplifier AF, which is V naught by Vs. V naught, from the definition of the gain of the basic amplifier, V naught is AVI, and Vs we have derived this expression for Vs, so substituting that here, so see that Vi and Vi will cancel out, and the gain with feedback AF we can express like this: A divided by 1 plus A beta. So that is our original expression, that the general expression for the gain with feedback that we derived in our first lecture on the feedback amplifier from the signal flow diagram, the general signal flow diagram of feedback amplifier. So in this case, the gain A is the gain of the voltage amplifier V naught by Vi, and beta is the feedback factor of the feedback network. Our next attempt would be to determine the input resistance of the feedback amplifier. So for that, here first we show the input resistance of the basic amplifier explicitly. So that is how we can show Ri, the input resistance of the basic amplifier connected at the input side between the two input terminals, and Vi is the voltage, input voltage that appears across this Ri, and then at the output side the amplifier can be represented by a voltage source, the dependent voltage source, which represents our output voltage V naught, and V naught will depend on the input voltage Vi times the gain of the amplifier, gain of the basic amplifier A. So A times Vi is our output voltage, so that is how it is represented. The output voltage is represented by a dependent voltage source, the voltage of which depends on the input voltage Vi, and that will come in series with the output resistance R naught. So if you look between these two output terminals into the amplifier, you see this output resistance R naught. So in total, this will be the equivalent circuit of the amplifier. Any amplifier can be represented by this equivalent circuit. So now with that, we can proceed to determine our input resistance RIF. Now first, the definition of the input resistance Ri is from the Ohm's law, voltage by current. So input resistance Ri is the input voltage Vi divided by input current II. So that is our input current II flowing into the input of the amplifier, and voltage divided by this current is our input resistance Ri. So from this we can also write the expression for RIF. RIF is the input resistance seen from this point, that is the input resistance with feedback, and it's seen by the signal voltage source. So at this point the input voltage is Vs, and so voltage here is Vs, not Vi, but the same current II is flowing. So RIF, the input resistance with feedback, we can express as Vs divided by II. So this is according to the definition for the resistance. Now, from our previous slide, we derived an expression for the signal voltage Vs, which was Vi times 1 plus A beta. So that is how we expressed the signal voltage Vs in terms of Vi in our last slide. So using that expression into the expression for RIF Vs by II, and Vs is given by this expression. So now here we have Vi by II, which we can replace by the Ri, the input resistance, and finally we get this expression for RIF, which is Ri times 1 plus A beta. So here we can see that the input resistance with feedback is given by this expression Ri, the input resistance of the basic amplifier, times 1 plus A beta. So that is our final expression for input resistance with feedback. What we can say here that the feedback in this case is increasing the input resistance. Ri is getting multiplied by this factor 1 plus A beta, and remember that this is the same factor by which the gain is reduced. The gain with feedback AF is A divided by 1 plus A beta. So the factor by which the gain is reduced, the input resistance is increased by the same factor. Another point to note here is that look at the connection. The connection at the input side is series connection, and we have an increased input resistance. And later on we'll see that whenever you have a series connection, that will cause an increase in the resistance, whether at the input side or at the output side. And whenever you have a parallel connection or shunt connection, that will result in a decrease in the resistance, whether at the input side or at the output side. So next we'll try to determine the output resistance of this feedback amplifier, and we'll see how the feedback affects the output resistance. So in order to determine the output resistance, it is not as straightforward like we have done it for input resistance, because for the input side we already have a signal voltage applied and a current is flowing in. So we can express the input resistance as the signal voltage divided by the input current. We can analyze the circuit and determine the input resistance. But for the output resistance, we don't have a voltage applied here, and our current is not flowing in. So in order to simulate those behavior, what we do, we apply a test voltage at the output side. When you apply a test voltage, so that will force a current I0 to flow into the amplifier. So now according to the definition of the resistance, we can say that ROF, the output resistance with feedback, will be the voltage at this point, which is Vt, our test voltage, divided by the current that is flowing in I0. So that will be our output resistance with feedback, that according to definition. But before we can analyze the circuit and determine this, we have to do some there are some more steps we need to carry out, or we need to take care of some of the things. So one of the things that we need to do to simplify the analysis is that we assume that the current that is flowing into the feedback network is zero. So this is to simplify our analysis to avoid the complicacy. we assume that the feedback network, it is sampling the output voltage, but it is not drawing any current from the amplifier. So that is a simplification, and this is we are doing in order to avoid the complicacy in the analysis. So when we assume that the current flowing here is 0, so this I naught, the current that is flowing here, the whole of this current will flow into the amplifier. So whole of this current I naught will flow into the amplifier through the resistance R naught. The other thing that we need to do is that we set this input signal voltage Vs to 0, because if you do not set it to 0, then Vs will have a contribution to the input current, and that current will generate a voltage, and that voltage will be amplified and appear at the output, and that will affect the output current. So that will change the value of the output current. So if you do not set this voltage to 0, the current that will be flowing here will be due to not only this voltage Vt, but part of that will be also due to this voltage Vs, and the final outcome of the output resistance ROF will be different if you didn't have this signal voltage Vs. So in order to get the accurate result of the output resistance, we need to neutralize all other effect that we can have on this output current, and one of these is the input signal voltage Vs. So we set this voltage to 0. So once you set this voltage to 0, that means these two are basically shorted, these two terminals. You get a 0 voltage when you short the two terminals. When two terminals are shorted, the voltage difference between the two terminals becomes 0. So with this modification in this circuit, now we can proceed to analyze the circuit and determine the output resistance with feedback. So once you have done that, now we can write KVL in this outer loop. So we are applying this signal voltage or test voltage Vt here, and this current is I naught flowing all the way into the amplifier through R naught, so giving rise a voltage drop across R naught, and then we have this voltage AVI. So the voltage Vt we can express as the same as V naught, and that is equal to the summation of I naught R naught voltage drop in R naught plus the voltage of this voltage source AVI. So that is the simple KVL. Now what is VI? Now if you look at the input side, since the Vs is set to 0, these two are shorted. Now you see that Vi and Vf are basically between the same 2 points. So these 2 points are the same, and the other common point is this between Vi and Vf. So basically these two are in parallel. So Vi must be same as Vf in magnitude, but they will be opposite in polarity, because Vi has a positive on this side and negative on this side, whereas Vf has a positive on this side and negative on the other side. So they must have the same magnitude, but they will have opposite polarity. So we can express this as Vi is equal to minus Vf. They just have the opposite sign, and Vf from the feedback network will be beta V naught. So Vf is beta V naught, and V naught is the output of the basic amplifier, which is here same as Vt, so we just write minus Vt. Now replacing this Vi for minus beta Vt in this expression for Vt. Finally, we get this equation. Now, rearranging these terms of this equation, this can be expressed like this. Now, from here, we can get an expression for the output resistance with feedback ROF, which is Vt by I naught. If you rearrange the terms in this equation, you see Vt by I naught can be expressed like this: R naught divided by 1 plus A beta. So that is our final expression for the output resistance with feedback. And what we see that in this case, the feedback reduces the output resistance, and it is reduced by the same factor 1 plus A beta. Note that the connection type at the output side, the connection type is a shunt connection, and as we have said in our last slide while deriving the expression for the input resistance, that if the connection is series, it will increase the resistance, and if the connection is shunt, then it will decrease the resistance, whether at the input side or at the output side. And here you see that we're determining the resistance at the output side, and at the output side we have a shunt connection and we have a reduced resistance. So since the connection is shunt, it is reducing the resistance, and it is reducing the resistance by the same factor 1 plus A beta. So this is an important parameter in the feedback amplifiers 1 plus A beta, which is also known as the amount of feedback. The greater is the amount of feedback, the lower will be your gain with feedback, and the more will be the change in your input and output resistances.